Okay, I think we can start. Perfect. So welcome everybody to today's version of the Air Center Networking Fridays, and we will be focusing on the EU project INNOAQUA. So let me start by sharing my screen. Super. I hope everybody can see it. If not, then I hope I get a message. But yeah, as mentioned, today we are talking about INNOAQUA, and INNOAQUA focuses about sustainable aquaculture practices for innovative seafood products. So I will be starting with a short introduction about the project, and then we'll dive deeper into the results that we have obtained so far. So you'll see the program here. These times are in universal times. And at the end of this session, we'll open for questions and answers, and a nice discussion, hopefully. So please, if you have any questions, drop them in the Q&A box. I think even the people live on YouTube that are following can put their questions somewhere, and we might be hopefully able to see them and answer them for you if we can. Okay, so INNOAQUA, the main objective of INNOAQUA is to make European land-based aquaculture more sustainable and more diverse. And we'll be doing that in this project by demonstrating innovative algae production processes that are focusing on circularity and digitalization. And then also we'll be using the developed algae into novel food products. So the whole project is centered around this technology backbone, and that starts with the cultivation of the microalgae. So here we are focused on two demonstration sites. One demonstration site is in Norway, and there we have the integration of salmon in recirculating aquaculture systems, and then algae in connected photobioreactors. So it's a type of land-based integrated multi-trophic aquaculture, or an IMTA. And then the same type of demonstration in Portugal, but there the focus is on the production of coal. And there they are integrated in this land-based IMTA with seaweeds. More of the details will all follow in the next presentations after me. Then when we have produced all these algae, we're looking into the processing of the algal biomass. And then it's not only the algal biomass that we have developed, but also the processing waste of the fish that is currently not used, that will be used to produce ingredients for new food products. So that you can see here, we'll be following a biorefinery type of process where the algae will be fractionated in well, the proteins, the lipids, the pigments, and other fragments that are interesting. And all of these fragments will then be used to develop vegan meat analogs, vegan fish analogs, but also hybrid products, and everything that cannot be used. And that's mainly going to be the carbohydrates. They will be used to turn that into food packaging. So that's the technology backbone, but to ensure that we are developing products that and food that is also interesting and that consumers actually want to consume, we have a good portion of our work on the social innovation side to make sure that we co-create the products together with consumers, and that we make sure that they're interesting. Of course, we don't only want to make interesting products, we also really want them to be more sustainable than what is currently happening. So for that, we have our sustainability analysis that we'll talk about later today as well. And we'll also look into the safety and regulatory aspects, especially since we're dealing with aquaculture waste streams as well. And finally, last but not least, of course, we will be talking about results that we're getting, such as today's event. We have a very nice consortium consisting of 16 partners, ranging from research institutes to small and medium-sized companies to large companies and other organizations. And they're divided over the whole of Europe. So we're, yeah, as you can see on the map, spread everywhere. And it's a 4-year project. We're currently in year 2. And so hopefully, if you stay tuned, there will be more results in the coming years to come. Just a quick, I'm the coordinator of this project, so if you want to reach me, here are my contact details. And if you want to learn more about the project that you won't be hearing today, then I advise you to look at our social media or our project website. Yeah, hope to see you there. So that was the quick introduction of the project, and now I would like to go to Markus, who will be talking about the social acceptance of algae-based foods.
Yes.
Stop sharing.
Thank you. Thank you, Dorinde. I'll share my screen. Okay. No.
Super. Good luck.
Nice. Thank you. Okay. Hi, everyone. Again, the INNOAQUA project, and I'm going to present the social acceptance of algae-based food. And I'm going to base this presentation on the systematic literature review that we have done in the project. My name is Markus Grendstad Rousseau. I work in NORCE. I'm a social scientist, and I'm in the researching group of Center for Modeling Social Systems. My background is in community planning and psychology, so I'm not one of the algae experts, but again, more on the social side. All right, so as I said, the agenda is I would like to present the literature review that we had. I want to go through the methodology of attaining articles. I would like to go a bit through the structure, as it is a structured literature review, and present some of the insights of the literature review. I would also like to end with present some of the ongoing research that we're doing right now, like the survey, and also future research, like just mention what we want to do with the results. Okay. So the methodology we used in the literature review to acquire different articles, that we started with a pre-screening process where we used the Python program to collect metadata of articles in ScienceDirect. And from this, we got around 830 articles, which we then used an API of ChatGPT to generate an evaluation of all of these articles. Then from ChatGPT, we got 327 articles, which we more traditionally screened with the human being. And then there was a more thorough review of 67 articles that was from the traditional screening. In this exploratory stage, we focused more on, well, we didn't know how much of the literature talked about specifically algae, proteins from algae. So we did all the protein sources, also like insects and lentils and beans. So then when we realized that there was enough articles on algae, we did the more topic-focused stage, where we identified 22 new articles from snowballing, which led us to a final sample of 27 articles with 35 studies, and then removing the studies that wasn't relevant for our case, we ended up with 27 coded in vivo. And here on the right, you can see the Prisma P flow diagram of the process. Here's the map of the total number of participations from each country. So you can see that most of the participants or the data collected is from the Netherlands, Germany, Spain, and Italy. And there's also quite substantial data collected in France, in Belgium, and Norway in the articles that we went through. In this map, I should say, or like clarify that it also includes both surveys and experiments like taste tests, and also interviews. So it doesn't depend on how resource heavy the survey is. So if you spend the same amount of resources on maybe 10 interviews, it's still going to be 10 interviews and then compared to 1,000 responses from a survey. So this is only the total number of participants, and not necessarily the resources that's been spent in the different countries. All right. So when we started with the literature review, we knew we wanted to look closer into action, food types, motives, and sociodemographics. And so let's see if I can have one of these. Yeah. So action, food types, motives, and sociodemographics. And the groups within these changed a bit throughout the literature review, as it does. But what we ended up with was actions that was establishing an expectation-based attitude and establishing an experience-based attitude. So we coded for if the cases looked into before or after people have tasted the product. Because we assumed that if you have never tasted the product, then maybe things like curiosity could be more prevalent because you haven't tasted it. But if it's on a more regular basis and you've already tasted it, then taste and price might be more prevalent. The food types that we ended up with, the food type structure, is meat analogs, fish analog, powdered meals, snack, grain products, hybrid products, general seaweed, general microalgae, and other. This was inspired by the concept products that we have in INNOAQUA, because what we wanted to do was to make literature review where people could go into this table, the structure we have, and then the food producers could look at what motives affected this specific food type. But it turned out that some food types, there's not a lot of research on. For example, it's very difficult to read, but hybrid products. No studies talked about hybrid products in establishing an expectation-based attitude. Most of the research was on grain products, general seaweed, and general microalgae. Then for the motives, it's, if you look in the second column, it's price, convenience, familiarity, lifestyle, ethical issues, sustainability, production method, health, sensory aspects, social pressure, and ability. And then in the third column, you can see what more subcategories went into these bigger categories. So in convenience, for example, we had accessibility, substitutability, so how easy it was to use the algae product in a familiar recipe by substituting out a product that you already know. Variety, snack form, or too much or lack of information. Yeah, so starting with some insights from the literature review, what we noticed quite early was there's the people express, or the studies express, that there's an intention behavior gap. So it's not necessarily what people say, like, oh, I intend to eat, or I'm willing to try this product. It's not directly translatable to what they actually do in the world. So this was something that you need to pay attention to. And then also it was difficult to differentiate between the different words the studies used. So some studies would use intention to try, or willingness or attitude towards trying. So, but you would get pretty different answers from if you're willing to try an algae-based food, or what your intentions are from a scale from 1 to 10. How much do you intend to try a product, or how willing are you to try a product could differentiate. So this was also difficult, and this is why we ended up with the structure that I explained earlier, to try to catch some of this, that you have an expectation based before trying the product and then after trying the product, or if you have tried the product before. And then also between trying and eating and adopting, you could get different answers. So like I said earlier, with trying, it could be more curiosity driving the willingness or intention to try. But eating and adopting, it would be more taste or price. Yeah. And then to the maybe more interesting parts, excuse me, is the motives. So we found that convenience and sustainability mostly increase positive attitude, The same goes for the product being healthy, and that the information about the product healthiness also increased positive attitude. But some studies looked into health interests, and this didn't show any clear effect. So more if the product is healthy, is a better variable to look at than maybe like if the participant is interested in being healthy. You also have, when we looked at production method, if the product was organic, this had a positive influence, and the different types of food that was most positively received was the pasta and the snack form. The dietary choices, we did not see a clear consensus between the studies if this had an effect on the attitude of consumers or the participants of the studies, actually. And then, as you might expect, the high prices decreased consumers' positive attitude, and the good taste increased positive attitude, and poor taste decreases positive attitude. But maybe a bit more interesting is that the information about taste and willingness to compromise on taste was shown to increase positive expectation-based attitude. So before people try the product, information about the taste and the willingness to compromise was a positive influence on the expectation-based attitude. Then you have, continuing on with the motives, the familiarity. And this, being familiar with the product or algae increased positive expectation-based attitude. But you got mixed results when it comes to experience-based attitudes. So maybe this could show that the people have had poor experiences or experiences with algae products that not necessarily want or like invites them to try it one more time. So that might explain why you have mixed results from an experienced perspective. Then on information, this showed this increased positive attitude when the benefits are communicated. So this is a healthier product, this is more sustainable. This is like sort of, this information is good. The innovative of the product was also mixed because it could both be a barrier and a driver for trying the novel algae products. So it could be, both scary and also quite intriguing, but this was mixed between the studies. And then we come to food neophobia, which means the fear of trying out new foods. It has, as you might expect, it decreases positive attitude, but food technology neophobia we found was a poor predictor of our attitude. So people didn't really care if it was highly processed or how the process of the technology was to create the food. It was, it didn't really affect the attitude. Then lastly, the motives, on ethical issues and social pressure, we didn't find a lot of data on this. So the sociodemographics, again, there was no clear influence on attitude, but young age and higher education usually increase positive attitude. But we were surprised to see that there wasn't really a big difference in different sociodemographic groups. Then lastly, the insights from the literature review that is going to be pretty important for us in our future work is that the effect might differ between groups with different nationalities, sociodemographics, and lifestyles. So as you can see on the map again, that the study covers, or the studies cover, quite a lot of different countries in Europe. And we saw that in some studies that did comparative studies, it can vary between nationalities, but it could also vary on a more sociodemographic and lifestyle level. Then finally, I would like to present like a bit of what we're doing and what we want to do. So the ongoing research is the survey, we're using the motives, the list of motives from this literature review as a base for the survey that we're sending out to Germany and Spain. And we're discussing these motives with food producing partners to get a final list that we're going to send out. And in the survey, we rank the motive on importance and satisfaction. So how important is it to you that the food is affordable, for example? And then also, to what extent do you agree, disagree with the food, that the food you had yesterday is affordable? So with these two, like the importance of the motive and also how satisfied you were with the product with this special like affordability or different motives. With these two, we want to use these two dimensions in an agent-based model. And I don't have time to explain a lot of what this is, but in short, in very short, it's a simulation. And the idea here is to, with the concept that we have now, it might change in the future, but to simulate a person going through a grocery store and choosing between a non-algae product and an algae product. And then in this simulation, we can test out different marketing strategies. So highlight the different properties of the product and also have different consumer groups that we could test it on and see how this matches up against each other. Yeah, thank you.
Thanks so much, Markus. Yeah, there will be time for questions at the end, so please put your questions in the Q&A box if you have any. And then we'll go on with the next presentation, which is going to be Pia.
Yeah, do you hear me?
Yeah.
Good. I'm gonna share my screen. Can you see it?
Yeah, looks good.
Okay.
Thanks.
Thanks, Dorinde. Hello, everyone. My name is Pia. I'm a researcher in the Marine Biotechnology Group in NORCE in Bergen in Norway. And here we have been working on the demonstration 1, which is coupling microalgae and salmon cultivation in land-based IMTA. So to give you a little background on this, so microalgae are a very diverse group of unicellular phototrophic microorganisms, and many of these microalgae species are rich in valuable compounds, such as protein, lipids, carbohydrates, or pigments. And they are therefore considered a promising novel feedstock for different commercial products, such as food, feed, pharmaceuticals, cosmetics, or bioplastics. And also their production is considered to be more sustainable than the production of other traditional raw materials, because as photosynthetic organisms, they can basically grow on light and CO2, and they also have high aerial productivities. And they're being produced either in these open pond systems or in closed photobioreactors, so they can be grown on land that is not suitable for conventional agriculture. However, so far microalgae production is still very expensive and also performed on a comparatively low scale. So that means that the actual application of microalgae is restricted to high-value products, such as food supplements or health products. So in order to implement microalgae also in other products, such as food and feed, it's important to create cost-effective but also environmentally responsible microalgae cultivation technologies. Now, the basic nutritional requirement for growing microalgae is carbon, nitrogen, phosphorus, and a couple of micronutrients. And the carbon is usually supplied as CO2 gas, while the nitrogen, phosphorus, and micronutrients are mostly supplied through commercial fertilizers. And the nitrogen is usually supplied in the form as nitrate, ammonium, or urea, and the phosphorus as phosphate salts. And these synthetic fertilizers are being produced either through chemical processing or through direct mining. So their production requires a lot of energy, and also their procurement costs money. So now many waste streams from industry, agriculture, or municipality often contain high amounts of nitrogen, phosphorus, and micronutrients. So this could provide an alternative source of these micronutrients for microalgae production. And this would also lead to a more sustainable and resource-efficient microalgae production, simultaneous waste treatment, and it could also contribute in decreasing the high production costs. So now within the INNOAQUA project, we wanted to test if we can use effluent water from land-based salmon production systems to produce microalgae. And the systems, the fish production systems that we were working with were recirculating aquaculture systems, in short RAS, which already allow a great degree of water recirculation and reuse by either removing or converting fish waste products. But still, these systems, they have nitrate that is accumulating in the rearing water. And they also usually have a daily water exchange rate of about 5% that is being released. And although the nitrate concentration is not super high in this water, if you have like really big fish production systems, the amount of water that's being discharged can become very large. And with that, also the total amount of nitrate that is being discharged. And if this water is being released into the environment, we not only use a valuable resource, but it can also contribute to eutrophication of the recipient water. But if we can use this water to produce microalgae, the nitrate can be removed from this effluent water because the microalgae will use it to grow. And at the same time, we can create a valuable product. Now, in order to have an efficient system here, where large amounts of water can be treated and at the same time enough nitrogen provided to the microalgae, we chose to use perfusion cultivation for the microalgae, which means that there's a constant inflow of the RAS water into the microalgae cultivation vessel, while at the same time the nutrient-depleted water is constantly being removed, while the microalgae cells are being retained within the vessel. So this basic concept we wanted to develop and test at a pilot scale. Therefore, we used one of these 2,500 liter RAS systems that was producing Atlantic salmon. Now, during a life cycle of salmon, the salinity of the water changes from fresh water for the young fish to brackish water, and then finally to salt water for the adult salmon. So in order to be able to produce microalgae all the way during the whole fish production cycle, we chose 3 different microalgae species which could grow at the respective salinities. And that was chlorella for the freshwater phase, Phaedactylum for the brackish water phase, and Nanochloropsis for the saltwater phase. And then in the next step, we placed a 25-liter photobioreactor next to the RAS unit. And that is a tubular photobioreactor where the microalgae are circulated through the tubes with an airstream. And also there's lights on both sides on the tubes, and the system also has an on-demand CO2 supply. Now, in order to start the cultivation, the reactor was first filled up with RAS water, and then we added some additional nutrients to allow the microalgae to grow to a certain starting density. So then we added the microalgae and let them grow until the nutrients in the water were used up. And at that point, we started the perfusion cultivation. So that means that the water that contains the nitrate from the RAS tank was constantly pumped into the microalgae bioreactor. And that was pumped via a filtration cascade in order to remove particles and also bacteria. But now to also provide sufficient phosphate, which was very low in the RAS water, and also micronutrients, of which we didn't really know the exact composition and concentration, we added an extra tank that we filled up with RAS water and where we added phosphate and micronutrients. And this spiked RAS water was then injected into the ingoing RAS water stream. And the amount that was being injected into the stream was so that the actual ratio of the phosphate and the micronutrients to the nitrate in this finally ingoing water would be the same that we have in our normal growth media. And that would be an NP ratio of about 5. So then in the reactor, the RAS water circulates together with the culture through the tubes, where the microalgae cells then consume the nutrients on their way up to the top. And then in order to, again, remove the water that is then nutrient depleted, the microalgae culture was pumped from the top of the reactor into the filtration unit. And the filtration unit that we used, therefore, was the one that you can see here. And that is a filtration unit that is vibrating constantly, very fast, which prevents that the filtration membranes get clogged by the microalgae cells. And this filtration unit then kind of splits the microalgae culture into two streams. So one stream contains the microalgae cells, which is being returned into the reactor, and the second stream is then the cell-free water, which is then the water that flows out of the system. Now, in order to have a constant biomass concentration in the reactor, because the microalgae keep on growing, we also had a constant harvest of microalgae culture. And the harvesting rate that we used here was the same as the growth rate of the microalgae. Yes, and so the volume of the RUS water that was flowing through this microalgae reactor in one day was 75 liters, which is about 3% of the volume of the RUS tank. And this cultivation mode was performed for at least 3 days for all the 3 species. And during this cultivation, we took daily samples of the inflowing and the outflowing water to analyze the nutrient removal capacity of nitrogen and phosphate. And we also took samples from the culture to analyze the biomass density and biomass productivities of the algae. Oh, sorry, I forgot. We also took some additional samples for to analyze the biomass composition, the elemental analysis, bacterial abundances, and bacterial community composition, in order to analyze the quality and the elemental composition of the microalgae culture and also of the RUS water. But these samples have not been analyzed yet. Yes, so this kind of cultivation we did 3 times, once during the freshwater phase of the small fish with chlorella, once during brackish phase with Phaeodactylum, and then during the saltwater phase of the large fish with Nanochloropsis. And here you can see the biomass concentration during the cultivation for the 3 strains in grams per liter, with first the starting up phase and then the following perfusion cultivation. And during perfusion cultivation, the biomass concentration remained more or less stable in the system, but you can see that the biomass concentration was different between the 3 microalgae species. So if we take the average value here, we can see that the biomass concentration for chlorella was the lowest with about 1 gram per liter, was a bit higher for Phaeodactylum, but it was much higher for Nanochloropsis with about 2.5 grams per liter. Now, each microalgae species also had a different growth rate, which was the same as the rate that the culture was being harvested. That was 1.2 for chlorella, 0.8 for Phaeodactylum, and 0.75 for Nanochloropsis. So chlorella grew actually much faster than the other 2 algae. And as a consequence of that, the actual biomass productivity, so grams per liter per day, was higher for chlorella than for Phaeodactylum. But it was still highest for Nanochloropsis, although it had a lower growth rate, but because it had this very high concentration in the reactor. And the reasons that we had this different dry weight biomass concentrations in the reactor was that the nitrate concentration of the RUS water was also different. So you can see that there was a constant increase of nitrate concentration first in the fresh water, then increased in the brackish water, and was much higher in the salt water, which is due that the fish were much bigger, so larger fish also then release more nitrogen into the water. So in order to also have higher biomass concentrations for these 2 algae, we would have had to increase the flow-through rate of the water in this system. And here you can also see the phosphate concentration of the ingoing RUS water. The lower bar with the stripes is the concentration of the original RUS water here. And then the blue bar on top shows the concentration it had after we added the extra phosphate before it went into the reactor. And here the concentration remained relatively similar, which means that these NP ratios that we aimed for 5 was only reached for chlorella, but it was higher for Phaedactylum and Nanochloropsis, which means that for them there was actually less phosphate compared to nitrate in the medium. And now in this figure, we can see the nutrient removal capacity for each strain, in pink for nitrate and blue for phosphate. So chlorella could remove 99% of the nitrate, but only 90% of the phosphate, which means that here we could actually add less phosphate into the inflowing water. The Phaedactylum removed 100% of both nitrate and phosphate, while Nanochloropsis removed 100% of the phosphate, but only 80% of the nitrate. So this means there was still nitrate coming out here in the system in the water. And this could have two reasons. One could be that the biomass concentration in the reactor was not high enough with regards to the nitrate concentration. So there weren't enough cells that could use up all the nitrogen on their way up through the tubes. Another reason could be that the cultures were actually phosphate limited, so there was not enough phosphate for them to actually take up all the nitrogen that was present, which in that case means that we should add here more phosphate to the stream. Yeah, so what have we learned from this? So yeah, we could see that the microalgae actually grow very well on RAS effluent water, and also the concept of microalgae perfusion cultivation on a pilot scale worked actually really well. And also the nutrients could be removed from the RAS water, dependent on the microalgae species, between 80 and 100%. However, there's still a lot of things to do in order to improve this whole system, and in order to increase the biomass productivities of the microalgae and also the nutrient removal, and yeah, to kind of establish a very consistent system here. But it's a lot of factors that actually play into here, which makes it a bit complicated. Then it's also important that we do an analysis on the biomass quality to see, are there any bacteria in there, or would the microalgae accumulate heavy metals, in order to evaluate if this biomass can actually be used in other products. And finally, it's also important to do actually an evaluation if this concept actually makes sense from an economic and sustainability point of view. Yeah, thank you very much.
Thank you so much, Pia. Okay, so again, we'll keep the questions for the end of the session. So then we'll go to the next presentation, which is going to be Rui.
Okay, yeah, mute myself. Okay. Hope we are in presentation mode right now. Yes. Okay.
Yeah, perfect.
So, thank you. Hello, everybody. My name is Rui Pereira. I'm based in Portugal, but I work for A4F. A4F is a Portuguese company or a group of companies. We should say that it's very well known for our skill and knowledge on the algae production and algae developing and technology. But not just in microalgae as it used to be, but now also working on seaweeds, macroalgae, and also on fermentation and other aspects of this value chain. So within INNOAQUA, we are responsible for one of our package, in particular package 2, where you have the demonstration site that Pia already mentioned, and we are responsible for the demonstration site 2 that I'll be telling you about during this presentation. But I would like also first give you a little bit of context on why the development of this kind of systems is important for development of the algae sector, especially in Europe. People already gave you a nice rationale on the chemical part, on the value part of the biomass of the algae, but I'll give you this perspective also based on statistics and the world figure, let's say. So for those of you that do not know, actually, the algae and seaweed in particular are already a very important part of world aquaculture. Okay, these are FAO data, and you can see that almost 24% of the world aquaculture production, that we only think about animals when we think about aquaculture, it's already algae. And in particular, seaweeds. 36.5 36.4 million metric tons per year is the latest numbers from FAO. So very, very meaningful. Now, another interesting thing is that out of all these million metric tons, 98% actually comes from aquaculture. So the world is not gathering algae from nature anymore, even though in Europe we still do a lot of that for our small amount. But in the world, 98% of the algae comes from aquaculture, okay? Not from wild harvest. Now, if you put this in perspective, world against Europe, the orange that you see in here, I don't know if you can see my mouse. There's a way to point, but I don't know how to do it.
No.
But you see the orange picture. I guess there's a way to point with a laser pointer, right now. Now you can see it. So the orange by here, it's the world's production of algae, 99.93% against 0.07% that is what we are actually able to produce in European region. That is almost nothing. But actually, if you put this in perspective within Europe, most of what we produce is seaweed or macroalgae. A little bit is microalgae, but this is fits well with what you just said about the value. It's actually the value of the microalgae produced is only 1%. It represents 19% of the actual value of the production within the European Union in 2022. Okay, so in a very simplistic way, how does all these million metric tons appear? Where do they come from? Okay, we already mentioned that they come from aquaculture. There are essentially two pathways of aquaculture techniques, let's say technology. Ones that are sea-based and ones that are land-based. Okay, near shore, offshore doesn't matter, but this tries to simplify the different methodologies and the main characteristics that are common to things that are land-based or things or technologies or farms that are sea-based. Doesn't matter exactly the details. So most of the production we have worldwide is actually sea-based. It comes from Asia, okay, from China, from the Philippines, from Japan, from Korea, and it's sea-based in areas that look like this from outer space. Okay, so this is a picture taken from a region in South Korea, and it's a picture taken from Google Earth. Okay, and this is a picture from the Philippines. This is from China. So this is how most of those 36.4 million metric tons are produced nowadays. The only thing, another interesting thing is only 8 seaweed genera actually represent more than 93% of all that production. So all that production is based on very few taxon. Okay, so it's not easy to agree that something like this will never happen in Europe. Okay, for many different reasons, because of the space access, because of the characteristics of our shorelines and the sea and the coasts, because of regulations, because of many things. This will never happen. So in Europe, we really have to try to focus on technologies that are land-based technologies, and with the production sites that look more or less like this. This is actually a picture from one of our partners at INNOAQUA. It's at Nova. This is a nice picture from an IMTA place in South Africa, part of a EU project, Astral. And this is a picture of one land-based indoor production site from a company in Denmark that is developing intensive production units for seaweed that are actually completely indoor in control. So seaweed aquaculture, land-based, outdoor, indoor, and customized PVRs, and all the implications that this means has to be an important way to develop aquaculture of algae in Europe, including the seaweed. Okay, and as you see here, there are many thousands of species already identified and known, and we're only farming around 31 according to FAO, but most of what we produce comes from those 8 or maybe 10 or 12 species. So one advantage, a big advantage, or several advantages of these units, this kind of systems, is that we can intensify production, increase quality control, and so on. But also, very important, and bring this here, we can create synergies with other sectors like IMTA. This is what we are trying to do with INNOAQUA. We already mentioned this the example for the demo one with the Macroalgae, and we are trying to do the same with the seaweeds here in Portugal. So, work package 2 of INNOAQUA, it's this. It covers 2 out of the 5 operational objectives that we have in the project. I will be focusing, like I said, on this demonstration 2, where we are installing what we call a smart IMTA system for monitoring and adaptation in real time of integrated multi-traffic aquaculture, where we combine seaweed with salt, a flat fish, and a commercial operation. The main KPI that we set up for this system are these: so the amount of productive area, the volume of water that we are aiming to treat per hour, how much we can remove, or we think we can remove from this system, and the productivity, and also to be able to actually produce different species in the same system, even though right now we will be focusing mainly on one uva or 2 uva and gracilaria, one red and one green uva. So, but we don't want to do this just another, there's many, but just one more seaweed production unit where we have our bioreactors receiving water on a flow-through system, where we gather a lot of, produce a lot of biomass, gather a lot of data, then treat all the data, and have a nice publication at the end, and that's it. So we want to make this something different. We want to make this system equipped and prepared to work on a more real-time basis. So for that, within our consortium, we also have a team of people from INNOAQUA, engineering institution here in Portugal, mainly for research, but with a lot of experience working with companies and SMEs and assisting them in answering to their needs. So we partnered with INNOAQUA to develop LCA, that is our fish farm partner, to develop a system that could support decision-making in our seaweed production unit. So this comes together with a different terminology that was unknown for me a few months ago as a biologist, as you can imagine. It's been a learning process, but it's putting together what we call operational technology that works on the ground, close to our tanks, where we'll have the seaweeds growing, but also with information technology, where this technology works in the cloud, as we hear these days. So the objective is to actually move from a land-based seaweed production system that is relatively low-tech, as most of the ones that exist right now, to something that uses the technology and move to an IMTA or a system that is more technology advanced. And the idea is to make it more user-friendly. So all these sensors and all this technology is meant to help the people that are running the seaweed production unit to make decisions. So you don't have to be, at the end of our project, the idea is that you don't have to be a seaweed expert to actually manage that system. Because if you expect that more fish farms adopt this kind of technology in their systems, they will not be receptive to become all of a sudden move from experts in fish production to become experts in seaweed production. They will always focus on their primary goal, that is to produce fish. So when we mean that we need to make these systems user-friendly, users are fish farmers, and they need to have the tools to help them make decisions on how to run this kind of IMTA with seaweed. This gets more complex because we actually asked our engineering people a lot of questions and wish that we wanted to control. They come up with questions to us, thinking that we actually know how everything works. But in the biology, when you are working with living organisms and systems that are not so controlled, you don't know, you know in theory how things should work, but you don't know for sure until you actually do it. But again, this has a lot of technology being developed because we really want to set up a list of hierarchical parameters, and the system should be able to react with priorities to one or to the other according to the actual dimensions that we have to control. That is, if you want to, for instance, if you want to prioritize production of biomass, the unit should be running in one way. But if you want to prioritize the treatment of the water, and removing the maximum nutrients from the water, then the unit should be run in a slightly different way. So all these put together, when you actually ask one of those artificial intelligence generators of images to come up with how does our IMTA to produce sea lettuce with IoT and artificial intelligence management, how would something like this look like? The image that this problem generates something like this. So I'm not sure if you confuse the sea lettuce with the normal lettuce, but yeah, the picture looks very nice, and we saw this. Yeah, this is very exciting. It looks like a really high-tech IMTA system. But this is the concept. Now we actually move into reality, into real life. This is an aerial picture of the production site where we are installing the system in the north of Portugal. And the roadmap into reality is like this. So it's basically, and the experience that I'll show you today is basically the process, the experience on developing the process until the moment where we are right now. The roadmap is being site assessment. There's a lot of things that we need to cover in terms of where it's better to install a unit like this. Fortunately, C8 actually has quite a bit of free space around, not so limited, but still there are a lot of things to consider, and we already realize this is something that will be happening in any time we want to develop a system like this in other companies. So available area, there's quite a few, but we need to actually make decisions. So after one first round of discussions, initially the system was going to be here, then moved here, and then here, and then back here, and now we are back in this place. And all this is an iterative process, of course, with the people on the ground, because of the aspects, practical aspects, safety aspects, future plans that the companies outline for this site, restrictions of the technology. It can be on one side and the other, and all this has to be taken into account. So we move from one layout to 2 to 3 to 4 until layout number 9, and that's where we are right now. And all this with discussions, of course, with all the partners. It's drawings and decisions and dimensioning of all this instrumentation until we reach the final layout. Procurement phase, which we are at now, and we hope that in the beginning of next year we can actually start construction on the site. This is already starting. This is actually the final area where we'll be based, and we'll be constructing this unit. There's a lot of very informative discussions that actually make us think as biologists about how important is everything that we think is necessary, but all discussions with engineering make us prioritize what is actually really necessary and what is extra. And that's a very important exercise for us as well. So the end result is this kind of system. So it doesn't look anything like the artificial intelligence image generated. It's much more like familiar objects and things. I'm showing you these 3D drawings, not because they are nice and I like to look at them and see them, but because they're actually tool that's been used over the last few months to actually before going into the ground and actually start building and construction. All these tools are used to actually anticipate problems, very practical problems with the direction of the tubing, direction of the wastewater, trying to short or find the shortest way for electrical cables, and therefore maximize or minimize the use of materials and minimize expenses and the capex of a system like this. And the whole process has been very enriching, but also it's taking more time than initially expected. So main lessons so far, again, we are not so advanced in Demo 1, but the main lessons so far that we can share with you that have to do with the process, all this process of planning and engineering, interaction with all the parties, of course, key. And these parts include us as a technology provider and development, but also INNOAQUA and C8, our host that is receiving this in their system, and everything has to be compatible with an operational commercial production of soil that has tremendous obligations and rules that they have to respect. It's clear for us that it was clear from the beginning, but now it's even more that such a land-based system will not be a one solution fits all. So what we're trying to do is to create a process and the mechanism and the roadmap that can better be applicable for future reasons like these. But there's always have to be some room for flexibility and for adaptation of the civil unit to the particularities of the fish farm that we are working with. So that's very clear now. Multidisciplinary skills are, of course, of biggest importance because of all the different aspects that you have to cover. Engineering is critical for sure. Again, one solution fits all will never happen, but the process, we need to streamline the process and create a standard process of how to develop and implement something like this. Main lesson for us, engineering is critical, but it's slow. Fortunately, ours will go much faster than engineering projects. Okay, this is, and we are ready to make this like a law of physics by now. It's definitely our algae can go much faster than we can put together an engineering project. But it's been a learning process, and I think this is the right way to start and to prepare so that when you actually move into the ground, we'll cover much of the problems, we'll anticipate much of the problems, and things could go smoothly from the start. And this is everything I wanted to share with you. And again, I'm also open for questions at the end, like the rest of the colleagues. Thank you for your attention.
Thanks so much, Rui. Okay, then we go to the last presentation of the day, and that is going to be Carlos.
Hi everyone, let me share the screen. I think it's full screen now. Hi everyone, my name is Carlos León. I am Chief Innovation Officer of SUSTAINN. We are a circular economy and sustainability consultancy company based in Pamplona, in the north of Spain. And we are leading the work package 5 of INNOAQUA project related to sustainability and circularity assessments. So main goal of the work package is to evaluate the sustainability performance in the 3 dimensions: environmental, economic, and social. Circularity, and the last task is to perform regulatory and safety assessment of the proposed technologies, innovation, ingredients, and products to be developed within the project. So work package 5 has 4 different tasks. You can see the duration of all of them. And today I'm going to share with you main issues about the task 5.2 and 5.3 related to socioeconomic impact assessment and life cycle sustainability and circularity assessment. So regarding the socioeconomic impact, the goal is to perform the assessment at 2 different levels. The impacts resulting from INNOAQUA innovations as a project at the project level, and in another level to assess social and economic impacts from the ingredients and products to be developed within the project and potentially to be commercialized after the project or outside the project. So the economic assessment at these ingredients and products levels, and we'll see this a little bit more later, we will develop the following life cycle cost assessment technique, considering all the costs throughout the life cycle of the final ingredients and products, and the social impact assessment following the recognized references such as the guidelines for social life cycle assessment of products and organizations released by the environmental program from United Nations. Related to sustainability and circularity assessment, the goal is to perform this assessment at 2 different levels at the same as well. It's to analyze sustainability in the 3 dimensions, combining the socioeconomic impacts already assessed in the other task with life cycle assessment of ingredients and products. And so will perform this assessment as a project as well, and another level, ingredients and products, where we will perform life cycle assessment of different ingredients and products, and mapping all the processes and operations that are to be performed within the project. So with all of this, we'll combine the assessment in the 3 dimensions in order to get let's say an overall single sustainability score of the life cycle of ingredients and products, and in parallel we'll perform a circularity assessment of ingredients and products in order to align this assessment to the circular economy principles. So we have the from technology to market approach, because we think that we have to assess the technology development process at the lab scale, analyzing the different operations and processes and operations in the cultivation phase, in the extraction and processing of extraction of microalgae and different seaweed and macroalgae as well, in order to extract some ingredients, and as well to analyze the scale up of the operations, turning the structure into seafood products. So we think it's important here to do this assessment at this lab scale in order to detect or identify the critical parameters related to sustainability in the 3 dimensions and circularity as well, in order to prepare the scale-up processes and the later industrialization processes of the different ingredients and products that the project is going to prove a scale-up and send them to industrialization processes. Because, for example, if we detect that it's a lab scale or in a scale-up process, it's let's say we have a very important consumption of energy or water in a specific operation, we need to prepare the scale-up processes and industrialization processes in order to get the optimal solution at the end in terms of sustainability and circularity. So this, from technology to market approach, we will use this approach for both assessment of the 3 assessments: socioeconomic impacts, environmental impacts, and circularity impacts as well. And following the let's say the 2 levels approach of the assessment, this is more or less let's say a scheme that shows what is going to be the process for to perform this socioeconomic impact assessment. And in this case, we think that we need to know the needs and expectations from the different stakeholders around the development of these kind of sea products, in order to know what do they need about from sustainability and circularity impacts or information from the project or from the let's say eventually commercialization of these ingredients and products at the end. So as I mentioned before, we'll perform the assessment at 2 levels, at the project level and ingredients and products levels. As a project level, in these let's say 2 dimensions or combination of 2 dimensions, social and economic, we have chosen different categories, and we will work in the next months in order to define which are to be the indicators and KPIs about these impact categories that we have defined so far. So, for example, we will try to measure and analyze which is the waste and resources productivity from as a project level, considering all the, let's say, technologies and innovation ingredients products to be developed at the end, and which is to be the market opportunities and business potential of all the ingredients and products to be to put in the market. Regarding the social dimension, we have identified these main impact categories, like the amount of jobs that the implementation of the techniques or commercialization of these products could develop or could create the jobs. Some indicators related to the availability of alternative proteins with these kind of processes. There are some activities here in the project in order to promote or to increase or improve the skills of different stakeholders, and then there are some activities related to knowledge transfer about the findings and learnings from the project. And last one is which could be the avoided societal cost if we are developing and commercialization these kind of products, because in theory we are let's say developing some let's say products and proteins that with let's say a less carbon footprint, for example, for if we compare these products with conventional products that we already have in the market. As a project level, we would like to analyze which is the alignment and contribution of the project to international policies in this part, in the social and economic impacts. And we will analyze and we will identify and try to measure which is the contribution to a specific targets of the applicable Sustainable Development Goals, to the main relevant indicators from in the Green Deal and Farm to Fork strategy, and finally analyze if we could measure the contribution to some of the indicators defined in the resilience dashboard from the European Union. The resilience dashboards defines a broad set of indicators and is trying to assess the strengths and weaknesses of different member states in 4 dimensions. That is social and economical, green transition, digital transition, and social geopolitical. So we will try to see if the development of these kind of innovative seafood products and new alternative proteins could, let's say, contribute to this, to some of these indicators there. And so at the ingredients and products level, we will follow the life cycle approach. So for doing this, we need to work first mapping all the INNOAQUA processes that has to be developed from the cultivation, processing, extraction, and later the formulation of ingredients and products. And at this part, we will analyze the social impact of ingredients and products, following the social life cycle assessment technique, and the economic impacts of ingredients and products, assessing the life cycle cost of the different ingredients and products. And this information will be needed to perform life cycle sustainability and circularity assessment, where we are combining the 3 dimensions, the social, economic, and the environmental impact assessment as well. If we are going to the task 5.3, the approach is similar. So we will perform the assessment at a project level, and we have defined the environmental impact categories, the most relevant, and we will work in the next months defining the indicators. But the most relevant impact categories are of course, carbon emissions, and in order to define which is the, let's say, the reduction of carbon footprint that these kind of products could contribute, and could we will compare this against the conventional products already in the market that we are trying with some of these ingredients and products to substitute them. The water footprint as well, and the land use footprint in the same approach. Regarding circularity impact categories, we will measure the water recirculation and reduction or minimization of waste, and the valorization of different kind of waste that are going to be carried out all along all the operations and processes in the project. And again, at the ingredients and products level, we'll need information, let's say, obtained in the socioeconomic impact assessment, and we will perform a life cycle sustainability assessment and the life cycle circularity assessment, and we all need, again, the value stream mapping of all the INNOAQUA processes. And as a project level, it's the similar approach, and we will try to identify which is the alignment and contribution to international policies, the Sustainable Development Goals, Green Deal, Farm to Fork, and Resilient Dashboard as well. And in this case, looking at the indicators related to the whole sustainability concept and circularity issues as well. And for the life cycle sustainability and circularity assessment at ingredients and products level, we are developing a methodology that it could be, well, we think it could be useful for the ingredients and products developers after the project, and we are defining different steps and different activities to be done in order to get an assessment of sustainability and circularity of the life cycle of a particular ingredients or a particular product. So we are defining the different activities here, starting from the value stream mapping. This is the first activity we are working on, working with all the partners in charge of, let's say, the productive processes within the project, in order to map the different operations that have to be carried out in order to identify the different, let's say, arrows and resources and materials or substances that we have to use for a specific operation, and the different kind of ways that we are going to generate in every operation. After that, we will select the different circularity indicators aligned to circular economy principles, and we will try to measure circularity with, let's say, simplified material circularity indicators. After having the circularity assessment and in parallel, as I mentioned before, we'll perform the assessment of the life cycle in the 3 dimensions: environmental impacts, life cycle costing, and the impact, the social impact throughout the life cycle. And with these, we'll identify different specific indicators in order to get the kind of sustainability overall score of every ingredient and product. And with all of this information, we'll be able to identify the critical parameters for sustainability and circularity related to all the assessments that we have done so far, and in order to be able to perform the different sensitivity analysis against the critical parameters and try to identify risks and opportunities related to sustainability and circularity, in order to help the developers for the, let's say, in serial production, industrialization, and commercialization of ingredients and products, and try to prepare them to be able to perform different trade-off analysis, combining different scenarios and alternative solutions that could be done throughout the life cycle, like different raw materials, different suppliers, different distribution paths, or different kind of solutions of different processes in a specific operations as well. So as I mentioned, we are now working with the different partners, try to define these maps and identifying first the different operations. After that, identifying the raw material substances and resources that we need for a specific operation, the different kind of ways that we have to generate as well. And later we will quantify these different arrows in order to start with the conversion factors for cost assessment, life cycle assessment, in order to get the environmental impacts, like, for example, the carbon footprint and the social impact as well. Well, this is one example of one of the maps we are been working so far, and we are defining the process in the whole process for this task, for example, at the lab scale. And after that, we will identify which are the changes, if there are any, in the, let's say, pre-ingredients scale or industrial scale, and in the, let's say, to be prepared the developers for the commercial scale as well. So as I said before, the idea at the lab scale, because it's not so relevant if we are thinking about the impact of the project, because the lab scale, it's not, let's say, using large amounts of materials and all these things, but the important scales, the important phases could be the industrialization and the eventual commercialization scale. But it's very important right now to identify the critical parameters in order to, as I said, to preparing scale-up industrialization processes. And finally, let me invite you for the upcoming webinar next Tuesday, in which we are going to go deeply about this sustainability and circularity assessments, and we will try to explain more in detail which is the approach and the findings and the, let's say, the well, the work we have been doing and the work we'll do in the next months. And I can put the link in the chat later on. So thank you very much, and open to any questions, comments. Thank you.
Perfect. Thank you so much, Carlos. Yeah, so that was the end of the presentation part for today. I'm not so sure if there are already any questions generated on YouTube if people are watching. I see no questions yet in the question and answer box here. So if anybody has any questions, then please type them there. I have actually a quick question for Markus, because I was wondering if we're looking at novel, or not novel, but like food acceptance, so to say, and we're going to develop like a very nice vegan fish stick, for example. Do you think it is important that people actually know what algae are if it's made of algae, or as long as it is a brilliant product, people not necessarily need to even know what an algae is? So how much is algae awareness, so to say, going to be important?
That is a very good question. And I don't have any like data to point to, but from reading and doing the literature analysis, I would think that the properties, or at least the benefits, like, because this we found in the literature review, that the benefits that algae gives to the food product, I think those would be important, and those would be very good to highlight and tell people that this is actually, it's green and it's good for you. I think that would be important. I don't know how much of explaining what algae is and the process behind would help that. I don't dare to answer, but the for sure the health properties or the other benefits of adding algae. Yeah.
Cool, thanks. Anybody else? Any questions?
I also have a question for Pia, but I don't want to take a room for any participants.
Oh yeah, just go ahead, and in the meanwhile we have a raised hand.
There's one hand raised, yes.
I can't see it, but Greg, I see in the chat that you have raised your hand. So if you can speak out loud, then please do so.
Unmute.
Yes. Now we
Hello,
can
perfect. Wonderful. I'm sorry I missed the first half hour of your presentation, but it was an excellent presentation with a lot of information. And I'm with a startup company, Sea Ranch Farms, and algae and seaweed is basically going to be one of our primary products that we're going to be growing and utilizing for the sustainability of a sea ranch farm. There's great benefit with algae, be it, for biofuels or for feed for our produce, the products, seafood that we'll be raising, and for feed for humanity. And I just wanted to say I would like to obviously get more information about what you guys are doing and hopefully potentially working together, because everything that I've seen in the presentation is something that we will be needing for all of our systems. We're looking at using what's called live feed systems, producing our feed on site instead of, deplementing our oceans from our smaller organisms, and utilizing that to feed our product, be it multitropic 3D ocean farming is what we're looking at doing with RAS systems, closed containment systems, so that we're not causing detrimental effects to our environment. And I believe that I definitely want to connect with somebody and to further develop your concepts with our operations. I see great benefit in it.
Super. I think that the YouTube of this whole seminar, so to say, will be available, so you can watch back what you have missed. And other than that, I would highly recommend you to go to our website, INNOAQUAproject.eu. But if you have specific people here now that you say I need you, then just ask them quickly in the chat, and they can give you their contact details.
Thank you very much.
Cool. Any other questions? Nothing that I can see right now. Changing between boxes. But I think either Markus or Rui. No, you also wanted to ask a question before.
Markus wanted, right?
Okay.
Yeah.
Then shout, Markus.
Yeah, I don't know if it's a good question because I'm asking about algae, and I don't know a lot about algae. But when you scale, Pia, I see like the system with the fish and the algae, and when scaling, do you know which one, or maybe not the algae, but the facilities for the algae? When scaling, do you know which one will be the most challenging at like a higher level if you have like a huge
Do you mean if we want to
fish?
scale this whole thing up to like real kind of production scale, or?
Yeah, which one would be the problem first? Would it be the fish side or the algae facilities, if that makes sense?
Yeah, good question, because we have kind of planned to do that in the project as well. I guess at that point, I'm not sure if the fish production system would be ready for that. But the idea was to, because we do have this same reactor, which was now 25 liters. We have like the big systems in Mongstad, like 4 750-liter systems. So the idea was then to connect those big systems to the actual larger fish production systems.
Okay.
Maybe I can add to that, because I think, so there is, how do you say it? The RAS tanks that you saw in the presentation of Pia, they are from Marino Mondraslab, and they're more of a research facility. So they're not the biggest tanks that are already out there. Up to a certain scale, there is commercial production of fish in these RAS tanks, and then there is a lot of plans also by our partners to even go further, because generally the fish size that they go to now is a medium size, so to say, and then they go to sea for the big production. But there's plans to go to the real big fish, like the 5-kilogram fish, also on land. So there's still novelty in that, but at the same time, there's a lot of knowledge already on also land-based fish production. Commercial microalgae production is also already available. So I think the biggest challenge is really this integration and making sure that all the nutrients are met for both of the organisms, so to say, and the quality requirements and all that. And similar to what Rui was presenting about to automatize this, so to really have this digital technologies and sensors that are really doing the processing, because similar for Rui was saying, it's like, who's going to do it? Are the fish producers becoming microalgae farmers as well, or are microalgae farmers going to be fish producers? Probably also not. So they will need to work together, and that both the technology side for that and the collaboration side for that, I think, are going to be the challenges in the future.
Nice.
Yeah.
Thank you both.
I have something, but that's exactly the comment that I was going to make. So, like Dorinde is saying, if you want to scale up one and the other, there's already examples on how to scale up, and they are operating, no problem. The tricky part will be the integration. I mean, not necessarily the one that will be the problem first, but when you integrate, very likely there will be one that will be the priority, and the other one will be like a secondary system. And so, in this sense, now there's always one system that will not be operating in an optimal way. At this moment, I cannot see the way technologies and the integration is possible. I cannot see that both systems will be operating at their maximum optimal levels. Okay, so there will be one, and then it depends. Like Dorinde was saying, is the fish farmer operating a microalgae? The priority is the fish, of course. This is the most likely to happen. If that's the other way around, the police will need to prioritize the microalgae, and then the problems will be the fish. So there's not a straight answer for that, but the challenge is the integration, like you're saying. And there's something that will be like the priority, and the other one that is following, trying to follow as best as possible.
Very interesting. Thank you, Rui.
Super. Did we get any more questions in the meanwhile? I don't know if there was anything. No, as far as I can see, there is no further questions. So then I would very much like to thank everybody for being here today, to our presenters for presenting, for our audience for listening. As mentioned, if you want more information on the LCA, it's going to be already next week that we'll be sharing a whole lot more in the webinar specifically on this topic. And otherwise, visit our social media, visit our project, and, or email us. Happy to answer any questions there as well. So thank you for today, and have a great weekend when it comes.
Thank you.
Thank you. Thank you.
Bye-bye, guys.
Bye-bye. Bye.
Bye all.
Bye.
Bye.
Thank you.